Hello and welcome back to this series on mathematics of quantum mechanics. Today we embark on a journey where the rules of reality take on a whole new dimension. In this video we will be cracking open the second postulate of quantum mechanics, a rule that governs the probabilistic nature of the quantum world. You will learn about Born's rule, which translates those probabilities into real-world outcomes. We will even talk about wave functions and the mysterious phenomena of wave collapse. What happens when we observe the unobservable? My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this second video on the mathematics of quantum mechanics. We move ahead into this video to understand and talk about the second postulate of quantum mechanics. And if you're really wondering what is the first postulate and if you have missed it, I've put that first postulate video in details in the description box if you want, and if you have missed it you can go ahead and watch it. Well, the second postulate of the quantum mechanics is, I would say in a simple language, more or less it means this. The probability of measuring a system in a given state is given by the modular squared of the inner product of the output state and the current state of the system, which more or less is the Born's rule. Immediately after the measurement, the wave function collapses into this state. Now, this rule connects the wave function, which describes the quantum state of a system, to the probabilities of different measurement of outcomes. It essentially states that the absolute value squared of the inner product between the wave function after the measurement, that means the output state, and the wave function before the measurement, that is in the current state, represents the probability of obtaining a specific measurement result. So let us remember that this postulate actually introduces a seemingly abrupt change in the wave function upon measurement. Before the measurement, you know that the wave function can exist in a superposition. However, the act of measurement actually forces the wave function to what we call collapse into a single definite state corresponding to the outcome. Now, we will look more into this as we go forward with the video, but this is, I mean to say, just a kind of an idea what the second postulate tells. Now, if I want to draw a diagram and show you into a schematic diagram, that would be essentially much better. So what is the outcome of the Born's rule or the postulate 2? It essentially states that the absolute value squared of the inner product between the wave function, that is the output, and the wave function before the measurement current state represents the probability of obtaining a specific measurement result. So here I would like to show you, this is what the if I want to show it in a pictorial frame diagram, it would be like this. So this part, as you can see, that this wave function, this is actually before the measurement. So it exists in a multiple state. So you cannot say that this exists in what state. And the act of measurement forces the wave function to collapse into a single definite state. Now, if you look into it a little bit deeply, it also connects to something which is called a Fourier transform, which I have already explained in one of my video in details, the Heisenberg's uncertainty principle and Fourier transform. It is not a Fourier transform, but collapsing and determining into a single state. Now, the question is that this before measurement and after measurement, how does it relate to the Born's rule? So here is the question. How does the Born's rule help? So by taking the absolute value squared, we will look into it mathematically, of the inner product between the pre, that means before measurement, and post, that is after the measurement, where the wave function collapses, we get a number between 0 and 1. And getting a number between 0 and 1 actually represents the likelihood of obtaining a specific result. So remember, we are just talking of likelihood, nothing more than that. So from this pictorial representation and the second postulate, we come to several important conclusions. What is that? Remember, point number 1, the collapse of the wave function, remember, is not a physical process, but it is a conceptual shift in our understanding of the system state. Second, Born's rules, what it does, it provides us probabilities, not certainties, due to the inherent probabilistic nature of quantum mechanics. And what is that? This is the third one. These postulates form the foundation for interpreting and predicting measurement outcomes in the quantum world. So these are few important points. Wave function, you cannot see it really like a building or something is collapsing. Born's rule won't give you a certainty, it only will provide you the probability. But yes, these are important because they form the foundation for interpreting and predicting the measurement outcomes of the quantum world. Now, as you just saw, it is possible for a quantum mechanical system to be in superposition. That means it is possible to be in the exclusive states. Now, say for example, if I think you are all aware about this bra and ket notation, so nothing to tell on that. So if I take this one as the ket vector psi equals to a0 plus b1, then you might have a question that do you actually perform a measurement to see the system whether it is in 0 or in 1? What will I measure? Right, so what is the actual measurement? So the answer to this is that will you measure a 0 or a 1? I mean, so what will be the outcome? So the definition of Born's rule says that suppose we have a quantum system psi and at an orthonormal basis which ranges from phi 1, phi 2 and up to phi n, then we can measure this psi, whatever the quantum state it is, with respect to the orthonormal basis. That means we are measuring this quantum system with respect to orthonormal basis. That means what we are asking a question, which one of these states is it in? If you are measuring it in an orthonormal basis, that means it is similar to asking the quantum system which one of these states is in. Is it 0 or 1 or so on? And the probability of measuring of the state of this one, that is phi I, that means I number of states, followed by the notation p, which comes from probability, is given by this one. Probability of phi I equals to this squared. Now why it is squared, that is we just learned in the it has to be the square of the modulus. So I have taken the modulus, I have put in the orthonormal basis, I have put in the quantum state, and I have taken the probability on the left hand side, and I have just squared it. So I mean to say, overall this is what the Born's rule states. So what happens is that the Born's rule, it actually connects the abstract and the perplexing world, that means what we cannot understand of quantum mechanics, to our concrete and tangible reality. Tangible reality in the sense, what I am trying to tell is that what we see, what we measure, etc. So it offers an answer to a very fundamental question: how can the probabilistic nature of quantum mechanics yields the deterministic world that we perceive? So that is why you have rightly seen on the thumbnail, what I have put is that, is reality only a probability? So whatever the thing that we see in the abstract world, put it into tangible reality, most importantly to make it a measurable thing, what we find is a Born's rule. So it was initially proposed by the German physicist Max Born, and the Born rule provides a method in which we can actually determine the probability of getting a particular measurement. So this is something, that is why I told that it actually migrates, or it moves the transition from the abstract world to the tangible world. Let us go back and turn our pages of history and go back to 1926, when Max Born originally published the paper, and how does it look like. Coming up in the next part of the video, a very quick glimpse over Max Born's original paper. So here you can see, this is again, it is written in German, so I won't dare to pronounce it, but as far as my German goes, I think this is on 25 June, I think it should be 25th of June 1926, and the translation says, on the quantum mechanics of collision processes. Well, this is something great, and this is the original paper, and if you want to read the original paper and you know German, then I have provided the link to the original paper, which I have taken from a website. The entire description, in the description you will get the link, and you can download freely and you can read the entire 1926 paper where actually Born formulated the rule. Now, interesting enough, there are a few facts which comes up, that in this paper actually Max Born was trying to solve the Schrödinger equation for a scattering problem, and he was inspired by the Einstein's probabilistic rule, that is the photoelectric effect. And here you see he concludes in a footnote that the Born rule gives the only possible interpretation of the solution. And you see I have written in bracket, it is taken from Wikipedia, that the main body of the article says that this amplitude gives the probability. And here it is written in German, bestimmt, I won't pronounce that. So that is where it is provided in the footnote. So while the footnote added in a proof says that the probability is proportional to the square of its magnitude. So I mean to say that is how it is, and I mean to say it is put it up in the footnote. This is the original paper, and here you can see that it was Max Born and Walther Both. Again, sorry for my wrong German pronunciation. They actually got the Nobel Prize in physics. Walther Both was awarded, I would say, a Nobel Prize. He was basically a German nuclear physicist who shared the Nobel Prize in physics in 1954 with Max Born. And so both of them actually got awarded the Nobel Prize, and this is the Max Born's original paper, which is actually the Nobel lecture of December 11, 1954. And again, if you want to read that, I have also put this an English translation into the description box, and you could go ahead and read the original Nobel lecture of December. And the first line is very interesting, which says that the work for which I have had the honor to be awarded the Nobel Prize for 1954 contains no discovery of a fresh natural phenomena, but rather the basis for a new mode of thought in regard to the natural phenomena. This is great. That means he says that it is nothing fresh natural, but rather the basis which provides a new mode of thought in regard to a natural phenomena. It's a wonderful lecture. I have gone through that in English, translated good enough. You can go through that. You will find some very good, I would say, insights about what Max Born thought and about his way of formulating the Born's rule in quantum mechanics. Right. So we come back from 1926 now to 2024, and we need to get over a very important function, important concept, which is called a wave function, although most of you know, but still it is a good point to state this. So it is denoted by this Greek letter psi, and it represents the state of a system. Now, when we talk of a state of a system, it is actually a little bit different from the, I would say, classical state of a system. Classical state of a system gives you an accurate description of the position, momentum, etc. of a particle, but here it only provides a kind of a likelihood, what we say. So the Born's rule, I mean to say, how they are related to wave function, because in one common form it states that the squared modulus of a wave function that depends upon position is the probability density. So until you get a wave function, until you square it, you won't get a Born rule. So that is how it is related. That means the magnitude squared of the wave function, as you see, psi x with the modular sign squared, gives the probability density. Probability density in the sense it can just actually gives you a probability, might be the electron or the particle might be in that region. So given say for example a kind of a matter wave which has got two variables, psi x comma t, and if I ask you a question that where exactly is the particle, so I would try to answer this question in a very, very simple manner. Where would the particle would be? So there are two possibilities. First, as we saw, when the observer is not looking or the particle is not being otherwise detected, it can be anywhere. It can be everywhere. So I can say that x would range from minus infinity to plus infinity. Just an overview. Number two, when the observer is looking, that means the particle is being detected. What happens? The particle jumps into a particular position or a state which is given x comma x plus dx. And the probability will be given by this, which is again the square of the modulus. And this is actually called a process which is called a state reduction, or a technical jargon which is called the wave function collapse. So this is how I mean to say you can understand wave function collapse, although I will show you a much better a schematic diagram which will make things clear. So if I get the classical notion in a Cartesian coordinate, 2 points x comma t, and these are somehow denoted by two coordinates 2 and 4, where if I draw a quantum wave, I mean to say a wave which is waving like this, then the electron can be here, can be here, can be here, can be here. So that is why we say that it is denoted by the Greek letter psi, and it a variable quantity that mathematically describes the wave particles, and the psi square, or what is called the Born's rule of squaring the modulus, it is actually the likelihood of the particles being there at the time. Remember, it is fully probabilistic in nature, guided by Schrodinger's rule, so you cannot say that it is exactly here. That is the philosophical and the fundamental difference between a classical system and a quantum system. So having defined this, what we called is a wave function, again from this mathematical and simple definition, few points again crop up. What are those coming up in the next part of the video? First thing is that a wave function in quantum physics is just a mathematical description of a particle's quantum state. Now, quantum state can be anything. It can be spin, time, momentum, and position. There are other states, I mean to say you can define a pure state, eigenstate. I'm not going into those right now. This function is basically a complex valued, and if you go back to my playlist on mathematics of quantum mechanics, I have actually shown why it is complex valued and it is not a real number. There you can go ahead and watch that. Most importantly, the behavior of the wave function, definitely it is guided by Schrodinger equation, which is a time dependent as well as an independent equation, which shows how the system evolves through time. And lastly, according to the superposition principle, wave functions can be added together, multiplied, that we will come later when we look into quantum operator, by complex numbers into a place which is called a Hilbert space. Now, after covering what is a wave function, what are the important features, what keeps you in your mind is that how do we define what is called a wave collapse? And remember, this wave collapse actually leads to what we just saw in the last point, that is called quantum measurement. Let us look into the next part of the video. What do we mean by wave function collapse, and what do we mean by a quantum measurement? Now here you see this is again a kind of a very technical definition. It actually says that initially it is in a superposition of several eigenstates, and then it gets reduced to a single eigenstate. Don't worry, I will define later what is actually eigen is coming from a German word. I will explain you later. Don't get bothered about that. Just look into this beautiful diagram. So on the left hand side you see a lot of threads, blue, green and red and purple, those which are wiggling, and you really cannot say that which position it is. And when the collapse of the wave function happens, you see a sun, a beautiful rose, people playing and a tree. So this is just an, I would say, an analogy. So remember one thing, that before measurement a quantum system can exist in a superposition of multiple states. That means that it has a certain probability of being in each state simultaneously. Collapse actually forces the system to adopt a single state, and this state is a sun, a pine tree, a hut, a red rose, or it can be anything. So the collapse occurs when the system interacts with the external world. As long as I'm not measuring, it is in superposition. As long as the instruments or my eyes, anything comes into the interaction with the external world, often through the measurement process. So even though the final state is definite after collapse, we can only again predict the probabilities of different outcomes. So from here we move on to understand this a little bit in a better way. Now suppose that we have a hypothetical quantum system with several eigenstates. Eigenstates in the sense you can say that these are different states, and these are well defined. I mean to say, for example, it can be 1, 2, 3, 4 and so on, right? And what from here where we can say that suppose that the wave function of the system is psi, as we have noted it, is in a superposition of 1, 2 and 6, for example. That means I can say that this psi would be in C11 plus C22 plus C66. I mean to say these are actually what we are doing, taking a linear combination. So if we want to measure the momentum of the system, which involves applying the momentum operator on the wave function, the instant we make the measurement, we have understood that the wave function actually collapses to one of the three basis eigenstates, right? So we have taken 1, 2, 3, 4 and so on, and the wave function is in a system of psi, which is in a superposition of 1 to 6. Now what I am saying is that as soon as we make the measurement, the value of the momentum associated with the state collapses. So point number 1 is that if it collapses to 1, then the value for momentum associated with the state is measured. If it collapses to 2, again, then the value of the momentum is associated with the system is measured. And if it is collapses to 6, it will be the same thing. So this is, I mean to say, this is not a very rigid mathematical description, but yes, it tells actually what and how you can measure, and when it collapses, how do you actually find out the collapse position. So from here you can see this is a superposition state and this is an observed state. Again, we can conclude few important points which are a takeaway. First thing is that superposition of states is never actually observed. The system collapses to a single state at the instant the measurement takes place. That is why we call instantaneous. Third is that superposition can be interpreted as a description of potential measurement outcomes. That means what could be the potential measurement outcome that can be done. And most importantly, the state of the system after the collapse collapse takes place is the actual realized outcome. So from here we conclude that the collapse can thus be defined as a transition between the potential, that is superposition, and the actual. And I've already defined what is potential, that is superposition can be interpreted as a description of the potential measurement. Now we talked about wave function collapse. We saw that how it collapses, how it takes one single form of several eigenstates to one eigenstate. Now we come to the next important part, which is called a quantum measurement. Now what is that? It is very simple. From a mathematical point of view, applying Born's rule, I would say, and then the wave function collapse actually shows what is called a quantum measurement. Let us see an example. Suppose we have this kind of a, I would say, system, and it is defined that we measure absolutely on an orthonormal basis, which would be 0, 1. What will happen that the wave, so this plus, now this is important. If you have watched my earlier video, I would like to show you here, this plus actually comes from here, and this minus actually comes from here, and you can even combine the plus minus state into 1 upon square root of 2. So I have just taken this as the plus part, but if you really missed the video, I just showed you how this plus actually comes from. It's a conjugation, from plus and minus. So if we have this kind of a state and measuring it in orthonormal basis of phi 0, phi 1 at 0 and 1, then the state would collapse to this one with a probability of this 1 upon 2 and 1 with a probability of 1 upon 2. Now just hold on, you keep this 1 upon 2 in your notebook, or do you remember, because this is going to yield a very wonderful phenomena. But anyway, this is what we call quantum measurement, and I can show you much more easily. This is just like the flipping of the coin. So if you decide to measure the coin's case, for example, with the basis of this one plus and minus, then what will be the outcome? Again, for the plus, the probability will be squared and it would be 1, and with minus with a probability of 0. And if you now recall, we just mentioned right at the beginning of the video that Born's rule gives us a probability of connecting the abstract world to the real world, and we get the value of 1 and 0, and with this 1 and 0 we can do a lot of calculation. So I've just actually showed you this. Now if I go back from here and I take the general case of a qubit, which is a quantum bit of a system, I think I have explained qubit earlier also. Here you see we denote the qubit as A with a vertical bar 0 and B with a vertical bar 1, and we measure in the computational basis, then the outcome will be what? 0 with a probability of A square and 1 with a probability of B square. Now again I ask you a very fundamental question. What if we measure the basis with a plus and a minus? Then you will say I will do this plus minus, and this would result into A plus minus B upon square root of 2, which means that the outcome of the state will be this one, because I have to take a square. So this is actually what if I take a kind of a qubit system with A and B, then the outcome of the state will be A plus minus B with modulus squared whole divided by 2. Now you see here also, and earlier to this, we are talking about some kind of an outcome which is probability. That means there is a concept of probabilism coming up. Now I would like to show you a wonderful example which is a kind of a probabilism, but you will feel very happy because this will lead to something very interesting. Okay, so the thing is that in probabilism, in the earlier two examples, what you saw, that if I take a kind, these were the two examples, right? So if I take a kind of a basis which is plus minus and a different kind of a basis, so what we can conclude is that measuring in two different bases yields probabilistic measure. Absolutely no doubt on that. So yeah, you saw that. So you can actually show that that the only time we will, so these two examples shows that taking two different bases yields probabilistic measure. Now the thing is that you can actually show that the only time we will get a deterministic result when we measure in a basis that includes the state, this one. But since this actually is something which is very arbitrary in nature, from here we can get it, but this is again very arbitrary in nature. So from here we can conclude that measuring an unknown quantum state, will yield a result which is always random. So if it is an arbitrary state, it will always result in a random result. And also we can find that when the superposition principle and Born's rule are actually telling is that quantum mechanics is inherently random. So when you have an unknown quantum superposition, it is impossible to predict precisely which outcome you will measure. You can only predict the probability of the outcome. So this is what the probabilism means and what the Born's rule actually shows. But here you see that I have taken two different bases yielding in a probabilistic measure. And now I would like to show you in the last part of our video that if we use alternative methods, yet we get the same quantum measurement. And that is something very interesting about the quantum measurement of quantum physics. So here again I take a kind of a quantum system and an orthonormal basis which goes from phi 1, phi 2, so on. So from here I can obviously calculate as C1, C2 and so on, and the probability of measuring each state of phi I is given by this. So as simple. And after the measurement, what happens? The system or the entire system collapses to this one. Now we can, from this one we go ahead and we say that we can always write the state this as an orthonormal basis of this. I'm just repeating that. And from here we get this one. Now if I apply the Born's rule and get the probability of the measurement of phi 1, then what I can do is can use the probability rule, which I square it. From here I get this one, and from here I get this one. So you see this is a series of equations. Now you see, since phi 1 to phi n, that is the orthonormal basis, this is an orthonormal basis. That means it shows that all the inner products will be obviously 0 except this one, phi 1 I1, phi I to phi I. So that means we can conclude from here that this would also be equal to C upon I squared. Now you see that this system which we just saw that the probability measurement of phi I is given by this, these two are actually the same. So this is an alternative method, but it shows that the quantum measurement or the outcome is more or less the same. Now if I take another I would say state, which is 1 upon square root of 2 1 by I, you can do the calculation, which I will show in the next part of the video. The catch is that if I ask you this question, what is the probability of this state in the state plus, say for example, the answer will be 1 upon 2, 1 by 2, and if you take the alternative method, there also it will be 1 upon 2. So both of them are correct. However, I won't be showing into this part of the video. In the next video I will showing the calculation how this same thing using two methods will yield upon the same result. So that's all for today's video. I am immensely thankful for all of you who are watching this video. Please hit the subscribe button and click on the bell icon to get all the notification from Physics for Students. This is my email ID, and please do subscribe to my other channel where I'm putting up videos only on Einstein's general theory of relativity. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Please do put up your reactions and comment, and do not forget to subscribe to this channel, and Physics for Students will be soon back with more interesting videos. But till then, goodbye and do take care.